Hello, welcome back to some more Modern Algebra. Scott Hader, Modern Algebra Made Easy. This is my third take. The second one got interrupted by my roommate. He apparently wanted to move this piano into the living room, this piano thing with this stuff. He's going to make a bookshelf out of it. It's really crazy. Anyways, so yeah. Take number 3. Let's try this again. So this time we're talking about homomorphisms. And so that's the general equation we use for homomorphisms. Let's talk about the basics before we get into the proofs and theory and all that jazz. So we need to know to work a couple problems is this: that phi is a relationship between two groups. Is a relation between two groups, a group to another group. And to be a homomorphism, for phi to be a homomorphism, a group homomorphism, it has to satisfy this equation. Phi of AB equals phi of A, phi of B, for all A and B in the group, in the first group. And we don't use the star notation anymore. We're beyond that. We're above that. Ever since binary operation days. But if we did, this is what we would use. Like AB, that really means A star B, the binary operation for our group, G, and star prime, that's the binary operation for G prime. So if you notice, phi is a relation between G and G prime, so phi of A is going to be in G prime. Phi of B is going to be in G prime. Thus, our operation that we do between those two should be our operation that we use for G prime. So, star is for G, star prime is for G prime. So just keep that in mind. And I'm going to rehash a lot of this, so really don't worry about it. Just try to make sense of it while I'm saying it, and then hopefully at the end it will all click together. So, determine if phi is a homomorphism. And I just put this formula here because that's what you'll need to be referencing. So, let phi map the integers to the reals under addition, where phi of n is n. Phi of n equals n. So, I have here phi of a plus b, and that's phi of ab with our operation being addition for the integers, as well as for the reals. And now, it says phi of n is just n, so phi of a plus b is just a plus b. But a, well, that's just phi of a. And b, that's just phi of b. So, we started here, we got here, it's a group homomorphism, bam. So we're not going too in-depth right now, we're just seeing some examples, seeing how the problems kind of work, seeing how the computations work, and so forth. So next, this time we're relating the reals to the integers under addition. But this time, phi is the greatest integer less than or equal to x. It's like a floor function, if you remember. Basically round down to the nearest whole number. So I just showed a counterexample to show that it's not a group homomorphism. Take two real numbers, 1.5 and, hey, 1.5. Well, if you add those two together, you get 3. Wow. This line is so profound. It may take you hours to understand it. It's just so incredible. You just have to, I'm totally just joking. But anyways, so 1.5 plus 1.5 that's 3. And phi of 3, if we round down to the nearest integer, well, that's still 3. And notice that 3 is not equal to 2. Oh my gosh. And if you, another profound statement is that 2 is 1 plus 1. Well, the point of all this is that we can write 1 as phi of 1.5. So 1 plus 1 is phi of 1.5 plus phi of 1.5. And this shows that phi of AB is not equal to phi of A, phi of B. So I hope that made sense. If it doesn't, just let me know. Next up we got phi mapping the reals toss 0 to the reals toss 0. So just to review, that star, that just means basically exclude 0. So the real numbers are not a group under multiplication unless you exclude 0, because there's no inverse for 0. So our phi, in this case, is just the absolute value function. And so we take phi of AB, and we hope to end up with phi of A, phi of B. So phi of AB, that's the absolute value of AB. And if you'll notice, that is the same thing as the absolute value of A times the absolute value of B. And if you took a basic proofs course, you probably proved something along those lines, that these two are equal. But in this class, you'll just have to take my word for it. And if we notice the absolute value of A, well, that's phi of A, and the absolute value of B, that's phi of B. So, ta-da! It is a group homomorphism. Alright, so sometimes the group operations are not the same. I don't think we've done an example where they aren't the same yet, but we will. We're going to. And so homomorphisms relate two groups together, to one another. So we must respect each group operation individually. So just keep that in mind, and we'll work a problem like that here in a bit. So there's one thing that you need to know, and we're going to use this for proofs later, is that there's always at least one homomorphism, and it's the trivial homomorphism. Just like there's always one cyclic subgroup, the trivial cyclic subgroup, it's similar. So the trivial homomorphism, again, just like the trivial cyclic subgroup, it has to do with identity. The trivial homomorphism is mapping all the elements in your group to the identity in the second group, G prime, which we'll call E prime. So I'm going to elaborate on that in just a moment. First, let's learn about what the kernel of phi is. That's a very confusing thing to learn at first, in my opinion. But it's really not too bad, especially once you understand some proofs. So, once more, our homomorphisms map one group to another, so both have identities. That's a fact. Both of those groups have identities, and we're calling them, one of them, the first one E, and the second one E prime. So our second factor we need to know is that this is kind of an informal definition of the kernel of phi, and that it's saying that the kernel of phi is actually a subgroup of G, and it's the elements in G that get mapped to the identity in the second group. That's what the kernel of phi is. It reads kernel of phi like this. So just remember, kernel of phi is the elements in the first group that map to the identity in the second group, and they make together a subgroup of G. That's an important fact. So these are, in fact, elements in the first group. So, doing some computations here. Find the kernel of phi and phi of 25 for phi of z mapped to z7, such that phi of 1 is 4. So basically, for kernel of phi, one numbers in G, in our first group, get mapped to the identity in the second group. Well, if we're talking about the group of integers, or the group of integers mod 7, we're talking about addition as the operation. I think I elaborated on that in an earlier presentation, but just in case that's not clear, for integers, it's only a group under addition. So what numbers in Z are congruent to 0 mod 7? Well, I hope that you were thinking multiples of 7. So that's the kernel of phi in this case. And notice 7z, that's a subgroup of the integers. A little connection for you. And phi of 25, that's our computation we have to do. Well, 25 is 1 plus 1 plus, blah, 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 25 times. And since it's a group homomorphism, we can use our equation that phi of A plus B is phi of A plus phi of B. We just expand on that a bit. And this is 25 times again. And so really this is 25 times phi of 1, but phi of 1 is 4. So that really this is 25 times 4. And, well, that's 100. And 100 mod 7, because we're mapping to the integers mod 7, is 2. So phi of 25 is 2. So that's that little experience in some computations. Do we have another one here? Yeah, we have another computational one here. So kernel phi, again, and phi of 20. Get a little sip of water here. So we're also given that phi of 1 is this permutation here. And just to rehash a little bit from the permutations video, this reads 2 goes to 5, 5 goes to 7, 7 goes to what though? I hope you didn't say 2, I hope you said 6, because 7 goes to 2, which goes to 6. This is a composition of functions. So if you said that 7 only goes to 2, well, that's only taking into account this first cycle here. You also have to take into account the composition of functions. So 2 goes to 5, 5 goes to 7, 7 goes to 2, which goes to 6, 6 goes to 1, 1 goes to 4, 4 goes to 2, and 2 goes to 5, and so forth. So all that gibberish, just review from permutations basically. Back to homomorphisms, we want to see what integers map to the identity in the symmetric group of order 8. That's what the kernel of phi will be. In the symmetric group of order 8, the identity is just the trivial permutation. 1 goes to 1, 2 goes to 2, and so forth. And so we want to find the order of each element, first of all, to do this. So let's look at 1. 1 goes to 4, which goes to 2, and 2 goes to 5. 5 goes to 7, 7 goes to 6, and 6 goes to 1. We're just using this right here. If you don't see that, just comment and I'll try to elaborate a bit. No problem. So you can see that 1 has an order of 6 because it takes 6 permutations to get back to itself. So to see the order of this whole thing right here, well, sorry, let's back up a little bit. So basically, I did that for each of the numbers between 1 through 7, except 3, because that's not listed here. And they're all order 6. 3 and 8 are not listed, they're just order 1. Because, remember, if it's not listed, then it just goes to itself. 3 goes to 3 and 8 goes to 8. So, basically, these are all of order 6, and these are of order 1. If you look back at the permutations video, you see that to find the order of this whole thing, we just take the LCM of each of those, of each of the orders. And in fact, that's 6. So what does this mean? This means that if you take phi of 1 6 times, you'll arrive at the identity in the symmetric group 8 of order 8. So it asks us to find, so that's the okay, so we want to find phi of 20 here. So phi of 20 is again 20 is 1 plus 1 plus 1, 20 times. And again, since this is a group homomorphism, we can break it up. And notice I didn't put addition signs here. And why didn't I put addition signs? Because we're talking about the binary operation for the symmetric group of order 8, and that's a composition of functions. Remember, permutations, the operation is composition, basically. So I just didn't put anything. It's understood that these are composed of one another. So 20 times, and that's basically, I wrote it like phi of 1 to the 20th, which is kind of consistent with how I've been writing it and how I've seen it written. So, and we can write phi of 1 to the 20th as phi of 1 to the 18th times phi of 1 to the, are composed with phi of 1 to the 2nd. And I did that because 18 is a multiple of 6, which is basically going to give us our identity. Not basically, it is going to give us our identity in this right here, the identity permutation. So, and the identity times anything is going to be that anything, not times. Why do I keep saying times? Composed with that anything is going to be that anything. So, phi of 1 squared is the same thing as phi of 20. That's what phi of 20 is. And now so we just need to find out what that actually is. Phi of 1 squared, that just means we take this permutation 2 times. So that means 1 goes to 4, and 4 goes to 2. So 1 actually goes to 2. And take 4, for instance. 4 goes to 2, and 2 goes to 5. So you see 4 goes to 5 here. If we compose phi of 1 of phi of 1. Okay? So we do that for all of these and we get this permutation here. And we can write that as this product of disjoint cycles here. Again, this is all review from the permutations lecture. I'm not going to rehash that here too much, like more than I have, because I've got to save time for the proofs and stuff. And by the way, the kernel of phi is just basically all the multiples of 6. Because all the multiples of 6 will, if you do this 6 times, any multiple of 6, then you'll arrive at the identity. Okay? So let's keep going. Okay, so we're almost to proof time. So if we have a group homomorphism here, there's 4 handy facts that you need to remember, or that you should be able to reference at least, if you don't need to memorize them, maybe for your test. But if E is the identity in G, then phi of E is the identity in G prime. And we're going to call that E prime. And I already kind of stated that earlier, but I'm restating that for clarity purposes, and well, it was listed here. So, okay, the second thing you need to know is that if A is in G, then phi of the inverse of A is the inverse of phi of A. Third thing is that if H is a subgroup of G, then phi of H is a subgroup of G prime. If K is a subgroup of G prime, then phi inverse of K prime is a subgroup of G. So don't worry 1,000,000% about all these things. It's basically the point of all these things is to show you that the point of that phi preserves certain qualities in the structure of the groups. And what I mean by the structures, like, or the qualities of the structure, like, for instance, the identities and the inverses in the subgroups. So I hope you can see that relationship. Honestly, I'm not a professional at this stuff, but I talked a little bit in my last video, the direct products of direct products of finitely generated abelian groups. Wow. About like a structure, about how like the order of each element and so forth. So I'm still learning about what it means for the qualities of the structures of groups. But so anyways, these 4 points. My point is that these 4 points we're going to be using in our proofs. Okay, so finally to proof time. So the first proof we're going to do, and this is a really good one to remember, you'll very likely see it on a test. Really wouldn't be surprised if we have a group homomorphism, it is a one-to-one map if and only if the kernel of phi is the identity. So this is if and only if statement, so we got to go both ways to show this. So here's a proof. First of all, we're going to go the forward direction. We're going to assume phi is one-to-one, and we're going to hopefully show that the kernel of phi is the identity. So by the previous slide, on number 1, we stated that if E is the identity of G, then phi v is the identity E prime and G prime. So if you'll notice, any more E is mapped to the identity in E prime. So E is for sure in the kernel of phi. The only question is whether there's any more elements in the kernel of phi. If any other elements get mapped to E prime. And if there were any more elements in G that got mapped to E prime, that would contradict phi being one-to-one. Because you can only have one input for each output. So you can only have one element that gets mapped to E prime. That's by our hypothesis. So therefore the kernel of phi is only E. There's nothing else. Alright, so let's go the other direction. I psyched myself out there because I thought the rest of the proof was on that same slide, and it's not. It's on the next slide, which is good, because I was hoping to show that part. Okay, so this time we're going the opposite direction, so I restated what we're trying to show. This time we're going the opposite direction. This time we're assuming that the kernel of phi is E, and we're going to show that it's a one-to-one map. Okay, so what do we got here? So how do we show something's one-to-one? Well, if it's one-to-one, hopefully in your proofs courses you've learned that you need to show that if the outputs are the same, that means that the inputs are the same. That's how we show that it's one-to-one. That's the process we use every time we want to show something is one-to-one. So we show that actually if phi of A equals phi of B, then that actually means that A equals B. And by the way, A and B are elements in our group. So if we have phi of A equals phi of B, if we multiply by phi of B inverse on the rights, then we end up with this. And phi of B times phi of B inverse is just the identity in G prime, which we call E prime. Okay, so let's continue. And if you remember part 2 from pre-proof time, this equals this. The inverse of phi of B is phi of B inverse. Okay, so now, since it's a group homomorphism, we can combine these two. But wait a minute, if phi of this is the identity in G prime, then that means AB inverse is in the kernel of phi. Well, if AB inverse is in the kernel of phi, and E is in the kernel of phi, and E is the only thing that the kernel of phi that's in the kernel of phi, then in fact AB inverse must equal E. Well, if AB inverse equals E, then just multiply by B on the rights. In fact, A equals B. You have to admit, this one is really cool. Especially this direction. I really like this proof. So, we've shown our stuff. A group homomorphism is a one-to-one map if and only if kernel of phi is E. So you really should remember that for test purposes and so forth. Alright, proof time number 2. So we got 3 proofs, by the way. So if you want to take a break or something like that. But we have another group, homomorphism. This time we want to show that if the order of our second group is finite, then phi of g, the order of phi of g is finite, and also the order of phi of g is a divisor of the order of g prime. So, if you look on the previous slide, I restated it here, so you don't need to do that. But number 3 stated, remember I stated all those 4 things that we're going to use periodically for these proofs. If H is a subgroup of G, then phi of H is a subgroup of G prime. That's just one of our handy facts that we can use. But now, G is a subgroup of G. Would you agree that G is a subgroup of G? So then we can just replace these H's with G's and rewrite this as if G is a subgroup of G, then phi of G is a subgroup of G prime. So now we know phi of G is a subgroup of G prime. Well, since the order of G prime is finite, which is necessary for the Lagrange's theorem, that tells us that by the Lagrange's theorem, we know that the order of phi of G divides the order of G prime, the order of the bigger group. Since the order of a subgroup divides the order of its larger group. And that's just Lagrange's theorem, so I think that should make pretty good sense. If it doesn't, just try reviewing Lagrange's theorem real quick, and still doesn't make sense, just holler at me. We'll try to clear it up. And only the last thing we needed to show that I showed that phi of G is a divisor of G prime, the order of G prime, but I didn't show that it was finite. But this should be pretty obvious, because if phi of G is a subgroup of a finite group, then its order must also be finite. Like, for instance, if you have a group of order 10 and you have a subgroup of that group, well, that subgroup is going to be a number of order less than 10 for sure, because it's a subgroup of the group. So a number less than 10 is definitely going to be finite. Of course, it can't be 0 or less, so it's got to be between 0 and 10. It's got to be between 1 and 10. Actually, the only possibilities would be 1, 2, 5, and 10. So anyways, it's finite. So, there you go. Alright, so our final proof here today is that if we have a group homomorphism, again, you're going to be so tired of group homomorphisms, you're going to be like, for real, dude? Group homomorphisms again? This time this is another possible test question. You should really probably study this one, where the order of G is prime, and show that it must be either the phi must be the trivial homomorphism or a one-to-one map. And so the key to this proof is to look at the kernel of phi, and this proof can really show the helpfulness of the kernel. So, if you remember, I stated that the kernel of phi is a subgroup of G earlier in the presentation, and by Lagrange's theorem, it must divide the order of G. because the order of G is finite. It's a prime number, so it's definitely finite. So we can use Lagrange's theorem. So the order of the subgroup is going to divide the order of the group. Well, if you divide a prime number evenly, either we're talking about being that prime number or being 1, because those are the only numbers that divide a prime number. So the kernel of phi is either, if this order divides the order of G, then it's either itself G or it's 1, or the order is 1. Okay, so let's suppose that the kernel of phi is the order of G. The order of the kernel of phi is the order of G. Well, in that case, this is the trivial homomorphism. This is basically using the definition of the trivial homomorphism and the definition of the kernel of phi. If this is basically saying that everything in the group gets mapped to the identity in G prime. So if this doesn't make sense, just review the definition of the trivial homomorphism and the definition of the kernel of phi. Now suppose the kernel of phi is, the order of the kernel of phi is 1. Well, for sure we know that the kernel of phi is E, and since there can't be anything else, since the order is 1, then the kernel of phi is just E. So just to restate this one more time, if the order of the kernel of phi is 1, there's one element in G that gets mapped to E prime. For sure we know that E gets mapped to E prime, because that's one of our handy facts. And if there's only one element that gets mapped to E prime, then E is that only element. So the kernel of phi is E. And if you join that with proof time number 1, bam, phi is 1 to 1. So that's another one that I really liked. So that's all we got for today. Have a happy Thanksgiving. As always, you're welcome to leave comments, questions, anything. And I hope to talk to you guys soon. Thanks for all the positive feedback, by the way, this semester. I haven't had time to do any videos, but I've been reading your questions and feedback and stuff, and I really appreciate the support and everything. So take care, and I'll see you in a little while.